Hi students, today we are going to discuss one of the very important characteristic property of the ferromagnetic materials, namely hysteresis. So the word hysteresis is a Greek word. It means lagging behind. So what is lagging? Behind whom it is lagging? Let us see now. Lagging of magnetic induction B. Behind the magnetizing field H is called as hysteresis. Now you can see the simplified circuit of an electromagnet, which we have studied in the lower class itself. So this is a solenoidal coil. The two ends of the coil are connected now in series with a battery, key and a rheostat. Now a ferromagnetic block such as a soft iron or steel. So this is a soft iron or steel block is placed inside the solenoidal coil. Now the key is open. No current can flow through the coil. Is it not? In such a situation, when no current is flowing through this coil, means the ferromagnetic substance placed along its axis cannot attain any magnetic induction. However, if I will close the key and I will adjust the rheostat so that a minimum current is passed through the coil, then corresponding to the minimum current, some magnetizing field will be established in the solenoidal coil. Isn't it? That is called as H. So H is the external magnetizing field. What for it is used? It is used to magnetize the ferromagnetic substance placed along the axis of the coil. So this external magnetic field required to magnetize a given sample only is called as magnetizing field. And that magnetizing field H is proportional to the current flowing through the coil. So H is expressed the unit of ampere per meter, ampere turns per meter. So H is expressed in terms of ampere turns per meter. So this is a unit for the magnetizing field. Now what is the magnetic induction acquired by the sample is denoted by the symbol B. So B is called as magnetic induction or the magnetic flux density. Now using the rheostat, when the current I is continuously increased, so ampere per meter will also get increased. That is, the external magnetizing field strength also get increased. Like that, whenever you increase the current, there is a proportionate increase in the external magnetizing field. And again, there is a proportional increase in the magnetic induction. It is found that B also gets increased initially along with the increase in the magnetizing field. Then further increase in the current or further increase in the magnetizing field at one stage will bring the magnetic induction to a saturation value. Then afterwards there is no further increase in the magnetic induction. Even if you apply a very strong current and strong magnetizing field also, once the sample has attained the maximum magnetic induction, there is no further increase. It has attained a saturation. Understand? Okay. Now, what is actually happening? What is the atomic picture happening inside the sample? Let us see now. You look at, this is the sample. This is the sample of the ferromagnetic substance. Say steel or soft iron or simply iron. So this is an iron rod in the absence of the external magnetizing field. When no magnetizing field is applied, simply an iron rod is held in our hand. All the molecules or the atoms present inside the iron rod are represented by these arrows, because we have studied that each atom of a ferromagnetic substance also is having a north pole and a south pole. Each atom present inside a ferromagnetic substance is having a permanent dipole moment, magnetic dipole moment. So here each arrow represents one atom or the direction of a magnetic dipole moment of one atom. So these arrows represent the dipole moments of a group of atoms present in a small region which is called as domain. So there are so many domains. Can you see, my dear students? 1, 2, 3, 4, 5, 6, 7, 8 regions are there. So 8 regions or 8 domains are there. Now inside the domain you observe, inside each domain, the direction of the dipole moment is in the same. Is it not? Dipole moment inside a given domain remains in the same direction. Okay, in the next adjacent domain you see the direction of the dipole moments. They will be different from the first domain. But inside the second domain all the atoms will have the same direction of the dipole moments. So this is in the absence of an external magnetizing field. Okay, so these atomic domains, these are also called as magnetic domains or ferromagnetic domains. So when you keep a ferromagnetic substance inside a solenoidal coil and vary the current as well as the magnetizing field, what is actually happening? The orientation or the alignment of each and every atomic dipole magnet will be changing as per the guidance, as per the order given by the magnetizing field. Just like in a march past drill, the PT master is commanding left turn, right turn, about turn, like that, is it not? So we quickly turn ourselves according to the orders given by the PT teacher. Like that, as per the order given by the magnetizing field, the direction or the orientation of the dipole moment changes continuously. Understand? So now in the absence of the magnetizing field, all the atomic dipole magnets present inside the sample will be in different directions. And now when I pass current through the coil, a magnetizing field is applied. Is it not? So in the presence of the magnetizing field, what will happen to these atomic dipole? No, all the dipole moments will orient and align along the direction of the external magnetizing field. So I have taken first what will happen when H is positive. Is it not? That is, left end of the coil is positive, right end of the coil is negative. So I have taken H as positive. So when H is positive, all the domains will vanish. All the domains will vanish. Understand? And all the atomic dipoles will orient themselves in the direction of the external magnetizing field. Okay? So this is the first case. Now, if I will reverse the terminals of the battery, when I reverse the terminals of the battery and once again I will increase the current in the coil, now what will happen? H will also increase proportionate to the current, but the direction of H will be reversed. Why? Because when the battery terminals are as shown in the diagram, suppose if the current is flowing in the clockwise direction in each turn of the coil, I have assumed that the direction of H is positive. What will happen if I will reverse the terminals of the battery and once again increase the value of current? H will increase in magnitude, but the direction of H will be opposite. This only is called as what? Negative magnetizing field or coercive field. Understand? Sir, there is no negative magnetic field available actually. The magnitude once again increases, but the direction of the magnetizing field is reversed. Such a negative magnetizing field only is called as a coercive field. And it is exerting a force on each and every dipole moment of the atom. It is exerting a force on each atom or atomic dipole, okay, to turn back in the reverse direction. So this is the third picture when H is negative. Can you see that there is a 180-degree rotation of the atomic dipoles? All the right side orientation has become left side. Why? Because the external magnetizing field is now negative. How I attained a negative magnetizing field? Just by reversing the terminals of the battery, that's all. So that now in the first case when the current is clockwise means when I reverse the terminals, what will happen to the direction of current in the coil? It will be anti-clockwise. So according to the direction of the current flowing in the coil, each and every atom present inside the ferromagnetic material is strained actually. It is strained. It is in a state of strain. It will turn left, straight up, straight down, right, then rotate left, right. Like that it is oriented in different directions according to the current only. So the direction of the magnetizing field depends on the direction of the current in the coil. This is an introduction before understanding what is hysteresis, my dear students. Now only the main topic hysteresis we are going to learn. Now the relationship between the magnetic induction acquired by the specimen and the external magnetizing field. This relationship is explained graphically. This graph is called as a BH curve. Okay, BH curve. Or this is also called as hysteresis curve. Now initially let us take that when the current in the coil is 0. When current is 0, then the magnetizing field H also will be 0. So that is represented here at the origin of the graph. Understand that? So when H is 0, there can be no magnetic induction acquired by the sample. Therefore, this is the point. I will take this point as A. So, the point A at which H is 0, B is also 0. Okay, now I am going to increase the current in the coil. So that proportionately who will also increase in the positive direction? Magnetizing field. So, H also will increase. So, I will take that the H also is increasing like this, okay, and you can see that as the value of H increases in the positive direction, now these are all the various points. At one stage what will happen? Saturation will be attained, okay. So H is increased but the magnetic induction attained saturation here, okay. Here itself the saturation is attained. So this point I can take it as C. From A up to C, you can very well understand that as the value of H is increased in the positive direction, the value of B also has increased in the positive direction, okay. So this is the point where the saturation is attained. Now what I am going to do is, using this rheostat, I will once again decrease the current back to 0. Initially I increased from 0 to a maximum current, is it not? Now I will return back such that the current decreases from a maximum to 0. Okay. Now what is happening? The curve is not retracing the same path. It is not retracing along a C to A in the same path. Rather, it is coming along a different path. So what is that path? It is found to retrace along some other direction like this. So this point is D. So from C to D, it is retracing in a different path. Now I find that when H was decreased from maximum to 0, I expected when H has become 0, B also will become 0. But actually, as I expected, it is not happening. Is it not? The curve has retraced from C to D instead of returning from C to A. Is it not? When H is 0, actually B should be 0. Anyone will expect. But it is not happening in the ferromagnetic material. That means this portion AD is positive. That is the B. The magnetic induction is still remaining inside the sample even after the external magnetizing field has become 0. It's wonderful, is it not? So, even after the external magnetizing field, which is the cause for the induction, that is the cause. When it has become 0, but the effect has not become 0, still it is remaining inside. Some magnetism is retained. We say when we retain some explanation given by the teacher for a longer period, then the teacher will say our retentive power is high. Is it not? Like that, this ferromagnetic sample is retaining some magnetic induction inside itself, even when the external magnetizing field is 0. And this portion AD is called as remanence. So AD is called as remanence. So this is also called as residual magnetism. Residual magnetism. So some magnetic induction is still remaining inside like residue. That is why it is called residual magnetism. That is also called as remanence. And you take two different substances like iron, steel, soft iron, like that, different ferromagnetic substances. According to their intrinsic properties, the remanence will be different. So the property of the substance, due to which it retains the magnetism, this property is called as retentivity. The property is called as retentivity, and the quantity stagnant inside, remaining inside the material, is called as remanence. Both can be called same also sometimes. Okay. So this AD is the portion which is remaining inside. Now I want to bring the magnetic induction back to 0 somehow by some method. But when I increased H to a maximum and returned back, it is not possible. So what I think, by any chance, if I will reverse the current in the coil, or if I reverse the direction of the magnetizing field, is it possible? I am finding out. So my dear students, once again the magnitude of H is increased, but its direction only is reversed. Okay, I am going to reverse. I am going to apply a negative magnetizing field by reversing the current direction from clockwise to anti-clockwise in each circular turn. And I am commanding each and every atomic dipole to give back the magnetic dipole moment. Understand? So to give back the magnetic induction to 0. So when I apply negative magnetizing field, now I find that it is coming like this. And at some negative magnetizing field, the point D has reached to new position E, at which the magnetic induction is 0. So the point E lies on the left hand side of this graph, is it not? So the value of H is negative at this point E, and the value of B is 0 at this point E. So I have brought the residual magnetism back to 0 by applying a negative magnetizing field, and this portion AE is called as a coercive field. Coercive field is the negative magnetizing field. Okay. Now once again, if I take 2 or 3 different materials like ordinary iron, steel, or ferrite, or alnico, like the different ferromagnetic materials, and if I apply the same coercive field, the magnetic induction will not come back to 0. It is different for different substances because it depends on the intrinsic property of the substance. That property of the substance, due to which it will give back the magnetic induction by accepting a negative magnetizing field, is called as coercivity. So the property of the substance is called by the name coercivity, and the field which is negative applied to the substance is called as coercive field. Understand? What actually is happening in the atomic picture, this magnetizing field, when it is reversed, it is forcing the dipole moment of each atom to come back to 0, that is aligned along the direction of H. So that is called as coercive field, and the property of the substance is called as what? Coercivity. Now once again, if I increase the negative magnetizing field, again at one stage saturation will come. Okay, so saturation will be attained like this. Saturation will be attained, and once again the graph will be retracing Same like the positive cycle. You see here, first the graph was going from A towards C in this direction. And now it is brought along the direction D to C. Then it is by applying a negative magnetizing field, the portion of the graph is tracing from D to E. Then after that, it is coming to another point F. So E to F, where here saturation is attained in the negative direction also. Then after that, once again it will be similar to this, okay, like this. The graph goes and here and then here like this, okay. So we can take the continuous points. So this is C, D, E, F, and this point can be taken as G. H already we have used here, so I can take this as K. I also we have taken already current, so G, K, and this point is C. So this is back to C itself. Now you can see that it is a continuous path from A. So starting from A to C, H is positive. H is increase in the positive direction. Then C to D, H is decreased from maximum to 0. Then AD is the residual magnetism or remanence or retentivity. Then to bring this magnetic induction back to 0, a negative magnetizing field is applied. So the path is from D to E. At E, the magnetic induction is 0 and the negative magnetizing field is AE, okay, coercive field. Then when coercive field is increased in the negative direction, it reaches a saturation at a point F. And once again from the point F, the negative magnetizing field is reduced by reducing the current and it is brought to 0. And then once again it is increased in the forward direction. H is increased in the forward direction, so that the total graph starts from A, passes through the points C, D, E, F, G, K, and once again back to C itself. This is a continuous and closed loop, and this loop started from A, then up to C, then D, E, F, G, after that K, and then to C. It stopped at C. And this loop only is called by the name hysteresis loop. Hysteresis loop. Now here, what is to be understood actually, when this graph has completed one loop, what must have happened to each and every atomic dipole magnets present inside the sample? They must have been oriented through 360 degrees. Where they started from, that same place they have come. Is it not? If this is the direction of the dipole moment inclined, okay. So according to the magnetizing field, it will be rotating in several directions and finally it is coming back to the original direction. Is it not? So when the H is varied, its direction also is varied. Like this, it is strained. Now continuously when the current is increased, decreased like that, when alternating current is applied to the circuit, what will happen? This will be continuously strained in every second. Every second the current is changing 50 times per second. The direction of the current is reversed 100 times per second when the frequency is 50 Hertz. So what will happen? In 1 second 100 times it will be changing its direction up, down, left, right, like that. So each and every atom is now strained. As a result, the entire sample will be heated up. The sample, if you touch, means it will be very hot. This is because of the heating up or orientation change of the atomic dipole magnets inside. So my dear students, here we come to understand that always H is ahead and B is lagging. We have studied in LCR circuit leading and lagging, is it not? Here H is leading and B is lagging. When H has come back to its original 0 value, B is not ready to come back to 0. It is still retained inside or lagging inside. So this phenomenon of lagging of magnetic induction B behind the magnetizing field H only is called as hysteresis. Okay children, now you see A, C, D, E, F, G, K, C is called the hysteresis loop, is it not? So if you keep different materials, ferromagnetic materials inside the same loop, solenoid, and very H, the area of the loop will not be same. It will be different. One will be very thin and tall, another one will be very bulged, flat, or it will be very broad and thick. So the area of the loop is very important characteristic here. So the area of the loop is equal to the loss of heat, the loss of heat energy. Understand? And this is called by the name hysteresis loss. Hysteresis loss. I told you, is it not, each and every magnet is commanded, go left, turn right, up, down, like that. So in 1 second, 100 times when it is rotating means then naturally the material will be heated up and the amount of heat lost per unit volume. Lost per unit volume. Okay, that only is called as what hysteresis loss. So from this, one short answer question, first possible question is define hysteresis. The lagging of magnetic induction B behind the magnetizing field H is called as hysteresis. Second, short answer question possible, define remanence or retentivity. So the residual magnetism remaining inside the ferromagnetic sample even after bringing magnetizing field H to 0 is called as remanence. And the property of retaining this magnetism inside the material is called retentivity. What is coercive field or what is coercivity? The negative magnetizing field required, what for? To bring the residual magnetic induction to 0 is called as coercive field. And the property of the material, okay, to bring the residual magnetism to 0 is called as what? Coercivity. So from this, 3 short answer questions are possible, and this may be asked either as a 3 mark or 5 mark question. So this curve is called as BH curve or hysteresis curve or hysteresis loop. This closed loop is having some area. So the closed loop area is equal to the heat energy lost per unit volume. Understand? And that is called as hysteresis loss. I hope you must have understood well. Fine.